Cool. Yeah, it's exciting to be here. I want to thank the GitHub organizers to, invite me, and it's an amazing venue, and hopefully you have had fun over the last day and today. Always honored to present some of the amazing work from my awesome colleagues at Facebook. So what you'll see today is basically a bunch of really awesome people working hard on pushing the frontiers. So one of the main things I wanted to touch, and I want to get everyone excited on, is how we are pushing the frontiers of video understanding and why this is an important problem for moving towards general AI. So hopefully, by the end of this talk, you all, as developers, are excited about this space and are excited to understand a little bit more about the challenges that we are facing in having general AI and in understanding video. So let's start. First and foremost, taking a step back, one of the motivations why we are working on artificial intelligence is we want to push the frontiers. We want to make the field push cutting-edge technology in machine intelligence space, but also make it accessible to everyone. And it's kind of fitting that I'm here talking in the GitHub conference, because it's one of the themes there, too. So we want this technology to be accessible to everyone. Now, Facebook and its family of apps are being used by more than 2 billion people every day. And as part of this, we have something called the social graph. Now, you take that social graph, and one of the things that we are trying to do is building the AI backbone to make this graph semantic. What do I mean by that? Let's spend a minute on understanding how we take this social graph and make it semantic, and how that connects to video. So when Facebook started, it was basically from colleges and universities to connecting with people, right? So as part of that, the social graph was people interacting with people. And as part of that, using textual communication, writing posts, writing status updates, and then moving to richer media, which is using photos to express themselves. Now, of course, we are in the video revolution, so majority of the communication is actually still moving towards richer media and catching up with video and experiences in video. Now, that's the social graph. You have these hard nodes where people update their status, share posts, share images and videos and experiences. What the AI backbone is trying to do is understand this content. Now, we want to make sure that Facebook, as part of the integrity and safety, preserves people's safety, right? And we want to make sure that your experience is enhanced and personalized. So as part of making the social graph semantic, the AI backbone is trying to understand that this particular photo violates a policy, this particular photo is about food, or you're enjoying your vacation. This particular video is about running. In that particular case, this is the roof of our building 20. It's a garden, which is amazing. So that's the AI backbone that is trying to make this social graph semantic. Now, why do we need to do that? And what is the advantage of doing it and thinking about it this way? The main advantage is, if you think about accessibility. So we launched this feature called Automatic Alt Text, which describes photos for blind people. Accessibility comes in the forefront. The developers inside Facebook can now think about all of this content and reason about it in a way that they could not before. The same particular nodes, the virtual nodes that are created by AI, can be used to do better newsfeed ranking, to give results on search in a much better way, and to make Facebook a safer place. So this is one of the fundamental reasons why we in applied machine learning are trying to take this social graph and make it semantic in nature. Now, coming to video, as I said, a lot of communication is actually around video and consuming video, producing video, and so on and so forth. And there are some unique aspects of video on Facebook. So in this particular simple example, this is a video recording of someone experiencing the metro. You obviously have pixels over time, that is video. But on top of that, you have this amazing amount of metadata that is being produced, that is being given, which is they are liking this, loving this at this particular instance. And there are comments going on around, this is an awesome metro, these are the facilities, and so on and so forth. So not only do we have that video and the pixels over time, but we also have this very rich metadata that we can use to understand video. And that's just one of the unique aspects. And I honestly believe that understanding video is going to be key to connect billions of people to the content that is being produced. So if we don't build the right technology and the platforms and put it in front of the developers, at scale, we will not be able to understand this video content, and they'll be black boxes. So that's why I want to motivate all of you as to what challenges we have up in front of us and what we are doing to overcome them. Let's talk about a typical machine learning cycle. Hopefully, some of you here, or maybe many of you, have interacted with machine learning systems or developed machine learning systems. We always start with data. Currently, most of the state-of-the-art networks or state-of-the-art techniques are fully supervised or weakly supervised or semi-supervised. What does that mean? That means we want to add information on top of this data that lets the model learn something that we want it to learn. So it could be, this image is of a cat, this video is of someone skiing. So supervision is something that is useful. Or this is a post that you might like or not like, and so on and so forth. So that's, you add supervision on top of the data. Then you select a model. You basically say, I want to use a deep neural network, a convolutional network, or I want to use a simple logistic regression, or a sparse neural network, or a graded boosted decision tree. Any machine learning model that you think is actually sufficient or valuable for you to get the problem solved. You put all of these three together, and you have any platform that exists out there, and you train your model. In the training, you get some training accuracy. You basically test it. Hopefully, you have a test set that is mutually exclusive from the training set, no overlapping there. I know many people have been burnt by this. So now you have a model, you trained it on the training data, you test it. You test it, the numbers look good, then you push it to production. That's the deployment phase. That's where the real cycle starts. That's the first iteration. And to get to that, you have done a lot of work, but that's where the real big game begins, the real awesomeness begins. So now you have this full loop where you can test your model in production and see where it fails, where it performs well, and you inform the next model, the next version of the model, using the data where it fails, improving the model. So this is the active learning loop, and this is the machine learning cycle. Now, the best part for us as developers, and to make sure the rest of developers can actually do this really, really quickly and reliably, and making sure that all of these components are state-of-the-art, is what makes this job, and particularly video understanding, a challenge. Let me walk you through all of these components with respect to video understanding. So one of the things that we have built internally, and we talked about this publicly, is once you take a photo or a video, it goes to this platform called Lumos. What is Lumos? Lumos is basically a platform that runs on billions of images every day and videos every day, right? So it looks at these photos and videos and tries to understand what is happening. There are more than 400 visual models in the Lumos platform. So this is a computer vision platform that is used within Facebook by a lot of developers within Facebook. And the models that are trained on Lumos are built on top of hundreds of millions of images. You need these large-scale data sets to be able to train the state-of-the-art models and make sure the accuracies that you have are very high for production quality. Now, why is Lumos so important? If you think about the state-of-the-art networks in computer vision, they're deep residual networks based on convolutions. You train them for a specific task. But the reality is, we as developers, when we build these models or platform, we think of scenario 1 to scenario n. But as users, or as people who are actually using this for various products and various experiences, they will come up with scenario n plus 1. What happens then? Obviously, one of the things that you could do is train these models. Typically, in 2012, when we first started seeing the revolution of deep networks, it used to take days and weeks. Now we are reducing it to days and hours. I'll talk a little bit about what our contributions are there in that space. Coming back, you have the scenario n plus 1. So one option is basically to train another model. Now, this is all good. It will give you good numbers. But the reality is we need to run these models on billions of images and videos. So you cannot scale this for all the tasks at Facebook, for all the tasks in general. So what do? The nice thing about these deep neural networks, or the state-of-the-art networks, is they're hierarchical in nature. So you can actually, individually in the model, break it down to multiple steps. What is the advantage of that? So when you have a new task, you can take the representations, the intermediate representations, at various levels for your task. So you as a developer now can make a decision whether you want to go all the way to the extreme and train a dedicated model for your task, or you use the existing representations because they get the job done. To do this, Lumos actually gives you this capability where I say, I have all of these tasks. Let me take the existing representations wherever possible, or build new representations when I need one. And that gives you this sweet capability as a platform to find the spot where you decide what compute you want to throw at the problem and what accuracy is sufficient for you for your task to deploy in production and to put it in front of billions of people. So that is Lumos. This is what we are doing to make developers' job easy in understanding images, in actually reasoning with videos. And when I talk about images, I obviously talk about video is one way to think about video is set of frames. So we can use the same existing technology on images for video as well. So in Lumos today, we can collect training data, we can train a new model, and push it to production within a few minutes. So this is really cool because let's say you want to start with, I want a model as a developer to recognize fireworks that get uploaded to Facebook. You can do this within minutes, where you can go and say, I want to collect some data for fireworks. So if there are any posts, public of course, which contain photos or videos where there's a mention of fireworks as text, you can basically collect some data. And this will allow you to collect data that is not fully supervised, that's crowdsourced, that is basically using metadata around the posts. Once you have that, you collect, obviously, there might be a mention of fireworks, but the actual photo or video might not be of fireworks. So what we do is we actually cluster them using the visual representations that we already have. And now when a human has to annotate, they don't need to annotate each and every individual content, which takes hours or days, depending on the scale. So what they can do is they can actually use the clustering mechanisms that we have as part of Lumos and annotate one cluster at a time, where if they think that cluster is looking good for their task, they can actually have all of these images as part of training set as positive examples. So we have now taken something like an abstract problem of having a model for fireworks to something very concrete where the data gets generated within minutes. This is really crucial because if you have the right data, you can actually train the model. So in this case, we are actually going to go ahead and train a model. And when you're training the model, you always want to think about the final goal, not that it's a computer vision problem or a text understanding problem or a speech or audio problem. So what we have in Lumos is not only the computer vision representations, but representations for audio, speech, and text, which you can merge and then say, is this post about fireworks? Is this video about fireworks? And so on. So this is a multi-model. And then you click the deploy button. It gets deployed, and it's part of the Facebook Visual Cortex, which is set of all these 400 models that gets run on new images and videos that get uploaded. And you can immediately see what is the live distribution. So you can see what this model is doing in production and see that, oh, OK, the examples that are firing with high confidence are actually fireworks. So this model is good. And then you can also go and correct the data on the live preview and actually teach the model. So you have taken a computer vision problem or a machine learning problem, and you have simplified it into all of these tasks, and you have given the tools to the developers to make the best use cases that we are not aware of. We don't know what is the significance of dropping the accuracy by 1% and saving the compute by 50%, whereas the developers will actually know this much better. So that's Lumos, and we can take these models and apply it on videos. So this is an example where you take these representations and you take these models and run it on videos. And here you can see live videos being scored for various objects, scenes, actions, and so on and so forth. So now we have at least scratched the surface of understanding videos in terms of classification, which is what is this video about in terms of scene, in terms of object, in terms of actions. So that's Lumos, and this is basically a platform that is used by internal Facebook developers and used for various experiences, as I said, to make sure Facebook is safe, the integrity problems, to make sure it's personalized experience, you have personalized experiences, and to make sure that however you're connecting with people, you're connecting in the right way and making sure your time spent is actually valuable. So that was the data part. That was the platform where you can collect the data and train the models in an existing way, in a scalable way. We have also worked on modeling. So here is an example of a model that is actually on GitHub. The code and the model is called MaskRCNN. This is the state-of-the-art network for understanding images. So you can do this model actually allows you to do instance-level segmentation and recognition. I'll tell you a little bit what the capabilities are. So here is an example output of this network that when you give an image as an input, it actually tells you one among 80 classes where the class is, which pixels belong to that class, where it is, how many instances of that class are, and so on and so forth. So here you can see how rich the model is in terms of understanding the real scene, the chairs, the bottles, the table, the plate, and so on and so forth. So this is one model that can actually do classification, detection, segmentation, and going further, human pose estimation. So one of the important things that we have noticed is when you're trying to understand images or video, the first thing is to understand people in the images and videos. This actually exposes or allows you to build a lot of really exciting experiences once you start understanding humans, where they are, what activities they are performing, you can do much better. So here is an example of the same network, Mascar CNN, trying to do pose estimation. So here you see the output example of the pose of the person. And using this pose, you can actually start reasoning about what activities people are doing in images. This is an amazing amount of work from the colleagues at Facebook AI Research that have put this model and the code on GitHub, accessible to everyone else. So one thing I want to talk about is we have made a tremendous amount of progress in understanding images. What is stopping us from applying this in videos? Isn't it just like take these models and apply it on every frame of the video, and will it not work? Actually, it does. It's a reasonable way of thinking about thinking about video understanding as a problem. You take these models and you apply on individual frames and you see these amazing results. So here is another example of pose estimation and segmentation of someone performing acrobatics. And you can clearly see the segmentation works really well, and the pose estimation works really well. So yes, you can get very far in terms of video understanding by applying image models. Absolutely. The other way, another example here is this is an example we talked about F8, where we want to take these Mascar CNN-like models and make it available for the developers so that you can run it on device in real time. So here is an example where we took that network and quantized it and made it super small, run it at 10 frames per second on your phone, and it can do real-time pose estimation of people. So this is another direction which is very exciting research. And you can start making your camera understand a lot more of what it's seeing and building really exciting experiences there. So these are all models where you take the best image models and you run them on videos, or you quantize them and run them on your phone in real time. Here is another example where we can take face detection and make your experience of video watching much better. So how many of you have bandwidth issues? Like, we probably in Silicon Valley don't have that as a problem, but the rest of the world, many people in developing countries have this. So here is an example where to your left is a person encoded with normal video encoding, but to your right is a person encoded with smart video encoding, where you are actually encoding the faces. You detect the face and track, and you encode that face in a different way, in higher resolution. But the overall bit rate for the video is same, but the watching experience is much better because you have a lot more clarity on the pixels of the face. So you can take existing image-based models and go a long way with respect to video understanding and creating new experiences. Let's come back to where we started. So we talked about the platform Lumos. We talked about how we can have the best data and best supervision. We talked a little bit about the model, right? But what about training? So as part of recently, a few months ago, we actually talked about it publicly. This is the ImageNet training in 1 hour. For folks who don't understand, who don't know ImageNet, it's basically a benchmark in computer vision that revolutionized some of these models in terms of image understanding and deep learning. So here, initially, when we were training these models, it used to take weeks or days. But the ImageNet in 1 hour is an example where we did distributed training, and the folks in applied machine learning and infrastructure teams in Facebook have done an amazing job to basically bring the time down to 1 hour. Imagine you as a developer making a change, and it takes you days or weeks to know whether that change is successful or not. It's going to kill you. It's going to kill your productivity. It's going to kill your creativity. And it's going to limit how many things you can try, on how many problems you can try. ImageNet in 1 hour is a perfect example where infrastructure and developer time can be exponentially increased by bringing down the training time. So here we use 256 GPUs and brought down training a model for ImageNet to 1 hour. This allowed us to experiment significantly on the architectures for video. So a couple of benchmarks in video are Sports 1 million and UCF 101. These are basically tasks where, given a video, you're supposed to predict which sport among the 480 sports that are in the database, or UCF 101, which is 101 action labels. So usually, it would take months or weeks. Using the ImageNet in 1 hour work that is fully available on GitHub, on open source, that anyone can actually use, we are able to bring the time down to less than half an hour or less than a day for Sports 1 million. This has actually helped a lot. The second part, so training, the platform, data is great. But what about data in video? do we, as a community of developers, as AI, people working on AI, for example, have the right data sets and benchmarks to measure ourselves on video understanding? So we have found that the current data sets have limitations. They have limitations because in these particular examples, you don't need to look at the video to be able to predict that someone is applying makeup, or this is about someone kayaking, and so on and so forth. You look at the frame, and you're able to predict 90% there. So you don't need the additional temporal motion or temporal information. So how do we build data sets that actually get us closer to understanding video? That is not going to just by looking at the frame, we can predict what is happening, what actions are happening. That's an important question, and we currently, as a community, don't know the full answers. So a couple of things that I wanted to talk today were 2 efforts from Facebook. There are 2 data sets that we are going to make available for the open source, for the community at large to build on. One of this is SOA. I'll talk about it a little bit. And the other one is generic motions. Both of these data sets are efforts where we want the whole community to help push the video understanding frontiers. Why these 2 data sets, and what are they? SOA is one of them. Super excited about that. It stands for Scenes, Objects, and Actions in Video. There are some really nice attributes of this data set. I don't want to list, they're listed here. I don't want to go through the full list. But the high level here is many of the existing video data sets, they are small, or they might not be fully supervised, or they are the outputs of previous algorithms. But in case of SOA, we made a concentrated effort and invested significant amount of resources to build it to scale. It's fully supervised. There are professional annotators actually annotating these videos. And it has various other attributes that, when released next year, the community and the developers and the academic folks can actually build on. Here is an example of what the annotator does. So we have these short clips. It's 5 to 15 seconds clips. And the human reviewer, human annotator, goes and selects a bunch of open world tags. So we don't tell them, you need to confine to this dictionary. They basically look at the video, and they add information, tags for objects, for the scene of the video, for what actions are taking place in the video, and in a free-form way. So the dictionary is open. There's our professional annotators. The videos are short, and it's a multi-target, multi-class problem. And the data set is large. We are aiming to touch 1 million and many, many classes for all the 3 dimensions. Here is just a histogram plot. On the y-axis is the frequency, and on the x-axis is various labels. Obviously, unless you have a magnifying glass, you can't see what the text is or of the concepts. But what I want to emphasize is you have a very long tail of the dictionary. So the most frequently occurring tag or concept in video in object is a person. There's no surprise there. But you have a long tail of the objects that occur in natural videos, of the kind of actions that happen. If you take a simple action like biting, it's about a human or a person eating a sandwich, but a dog biting another dog, or a cat biting something else, the toy, and so on and so forth. So you have actions, and when you combine it with objects, you have a combinatorial explosion of the kind of things that can happen in real world. That is one of the reasons I am super excited to unlock video understanding, because it gets us one step closer to the general AI problem. And SOA is one effort where we are trying to decouple actions, objects, and scenes so that we can actually evaluate models. Are they really good at understanding video? Or are they just looking at some visual patterns and saying, this is kayaking because I see a kayak and a person. But the real deal is you need a person actually kayaking to make it kayaking. There are some initial results and findings. We are going to push this as a challenge for anyone to compete, to actually train models on top of this data. This is the first time we are actually making the public videos available for others to build models on. We have some initial results on architecture search. We have done a significant study on what models to build. Should it be limited to RGB, or should we have motion information as well? Should we pre-train on other tasks and train on this? So there are some initial, lot of architecture search and work that we have done. And the learnings, the high-level learnings, this is a bit new. This is off the. Let me just say, this is not fully scientific yet because we need to do a lot more experiments. But the initial learnings are the variants for doing action recognition or understanding temporal information. You need optical flow. Optical flow seems to help a lot. pre-training on large data sets and then training on this seems to help a lot. And all variants outperform the frame-based model. This is very exciting. What that means is if you take models that are built on frames or images and apply it on video, they fall short compared to actually building models on video. That's really good, because video understanding is not about looking at snapshots and making decisions. Video understanding is understanding the motion over time. And we have some really exciting results on models that take minutes but are super accurate, but models that can actually run real time on your device that might be less accurate. And those are the mixed convolution models. The second data set I want to talk about is the generic motions data set. So here, again, if you just look at the existing data sets, they focus on activity recognition or they focus on certain aspects of video. But the real deal is to understand the fine-grained motion information. So let's take a couple of examples. So this is falling. Falling, a person can fall, a panda can fall, anything can fall. So you want to understand what does it mean to be falling. You want to understand what does it mean to be jumping. You can, obviously, in the natural world, in the real world, in natural videos, you will have people jumping or cat jumping. But you want to understand jumping irrespective of what object is performing that action. So the generic motions data set is decoupling the information, the action recognition, or the actions from the objects. Here is sliding, for example. And here is, obviously, a presentation is not complete without a cat in the videos. So here is a cat actually sliding and falling. So one of the exciting things for us when we were building this data set is to basically ask the question, given a short video, in this case, these are GIFs, if we have multiple actions happening in the video, can we build models to understand this? And can this then help understand videos in general? So this is the generic motion data sets. And there are some unique aspects of this data set as well. It's focused on motion. It is generic to different objects. If you think about jumping, we don't want to associate it with just animals or humans. We want to associate it in general. So there are other different aspects. Like I said, these are GIFs. They're small, so you can train models. You don't need crazy amount of resources, which is one of the things that we are excited about. And dataset is multi-label. So when you have an example, you not only have one label, you have multiple labels, so that you are actually understanding multiple things in one go. There are some preliminary results. And the exciting thing about these results are you can clearly see a huge gap between models that are looking purely at pixels and models that are actually incorporating motion. So flow is basically optical flow that incorporates motion. And when you combine it with appearance, you have much better accuracy. So clearly, the dataset is trying to push or trying to make use of motion to be able to do well. And that is one of the key things, in my opinion, to understand video. And when we start understanding video, we start making our cameras, we start making our cloud, we start pushing the frontiers of AI. Because otherwise, we will only get stuck in understanding one snapshot after another, but never understanding the real world. So we at Facebook really are excited to keep on pushing the frontiers, but also make these things available to the developer community. These are just a few examples coming from the Facebook AI Research Group, or the Applied Machine Learning Group, or the Infrastructure Group, and many, many other groups at Facebook that are in the center of the AI world, that are basically in the hands of developers, so that they can also push these frontiers along with us, and it's not just us pushing them. That's it. Thank you.